Alright, section 3.5. This section is going to be called Understanding Equations with Two Variables. Most of what we've been doing with equations so far this semester is just, the equation only has one variable, usually x, and we're just looking to solve for that variable, figure out what x would equal in the context of that equation. So going back to, I believe this is section 3.1, just to kind of, as an example. Look, this is what we've been doing a lot. Taking an equation that only has one variable, even though it might appear in more than one spot in the equation, but just trying to get x ultimately all by itself and to figure out what x would equal, solving for x. And look, let's be honest, we've already kind of worked with equations like this problem that we did, for example. This equation had two variables, but with this word problem we were able to come up with like another equation, and kind of like when we were able to merge the two of them together, we were able to end up in a situation where we actually only had one variable to worry about at a time and solve for them. Like we had enough information in, say, this word problem to end up solving for both m and s. But where like the territory we're getting into now is just, hey, no word problem, here's an equation that has two variables in it, and normally those two variables are x and y. That's going to be like the vast majority of the time. Like those are the two variables you have, x and y. And we're not going to be able, so kind of cutting to the chase in a way here, one of the points I'm kind of getting to is that we're not going to be necessarily solving for anything. So we're going to be answering different kinds of questions, doing different kinds of things in this lesson anyway, and in the future when we're dealing with an equation that has both x and y. And just like this one with m and s, where m was like a number of Milky Ways and s was a number of Snickers bars, an equation that has two variables pretty much tells the mathematical relationship between those two variables. Sometimes x and y are just x and y, and sometimes the two variables actually mean something sort of real life, like here. It's not just a random m and a random s. These two variables actually represented something, and they had a relationship. Like this was kind of one of the relationships, just like this other equation represented a relationship between the number of Milky Ways and the number of Snickers bars going on, with Wendy. So anyway, also trying to build to where when you have two variables, okay, if you were to graph them, well, maybe we'll start over here. Because when you have two variables in an equation, normally you have x being a more independent variable and y being more dependent. So in this equation, y equals, whatever x is times -5 plus 3, and that's how you get y. So in a way, y depends on what x equals. So y is dependent on, like if you said x was 2, then y would equal something. Y would equal, I think, like -7. If you let x equal 2, okay, then whatever y would equal depends on whatever x equals. And I know it could work both ways, but especially when you have real life things, which we'll see here in a second, sometimes the two actual variables that you have, quantities, one will be more dependent on the other in a real life situation, which we'll get to that in a second. But first, let's finish this stuff where X is more independent usually, Y is more dependent. And another way to kind of describe it is like you input something for X, and then whatever Y would have to equal would be sort of like the output. Okay? Let's see here. Just didn't discard that. Good enough. And just really quick, the other things on this page is if you were to make a table with these two variables, normally what's on the left would be more independent. Wow. And the right column would be more dependent. So that's how it works with tables. Whether it's X and Y, or R and T, and P or Q, whatever the two variables are. I know it's easy with X and Y because they're in alphabetical order. But whatever's in the first column is usually your more independent variable, and whatever goes in the second column would be your more dependent. Same with a graph. If you were to graph this equation or make some kind of graph representing or the relationship between two things, and again, I know it's easy with X and Y, but whatever's more, whether it was X or T or N or whatever's more independent would go on the horizontal axis usually, and whatever was more dependent would usually go with the vertical axis on any kind of graph you were making. Okay? Okay, so maybe if you want to put more like notes, whatever would be, again, it doesn't have to be X, it could be whatever variable's going on, but that axis would be, and same with the table, okay? Maybe we'll do like some kind of abbreviation, independent, and then whatever would be there, whether it's a Y or whatever, doesn't matter. That would be the vertical axis in the second column. Anyway, we've lingered about that stuff probably too long. So here's what I was referring to. So here's a random sort of real life situation. Katie is raising money by selling boxes of cookies. Okay? So I know it's kind of just a quick, blunt description, but there's two variables happening in this scenario. There's two quantities that can vary, two things that have a number to it. So what are those two things? Katie's raising money by selling boxes of cookies. Isn't one thing how many boxes? Like that's a varying quantity. That's a variable, like the unknown varying number of boxes. And then there's also the amount of money. So wouldn't you agree that one of those is more dependent on what the other one is? What do you think? Which one of those two quantities is more dependent on the other? Well, hopefully you're thinking that your dependent variable is like the amount of money raised, and the independent variable would be the number of boxes she ends up selling, okay? So if we were to make a graph or a table, the number of boxes would be this left column, and on a graph it'd be the horizontal axis. And then the amount of money, those values would be in the second column of a table, and it would be on the vertical axis of a graph of some kind. All right, next example. Let's try to keep this moving at a good pace. Jennifer's setting up chairs for the dinner party. Again, I know it's not very detailed, but if you think about it, this scenario, there's two quantities, like things that you could put a number to. What are they? Jennifer is setting up chairs for the dinner party. Well, probably like the number of chairs, but what else would be a varying quantity in this situation? Maybe the number of people? So which one do you think, as she's setting up chairs, which quantity do you think is more dependent on the other? Do you think the number of chairs depends on how many people are coming, or do you think the number of people coming depends on the chairs? I think it probably works like this. Independent, number of people that are going to show up or that were invited, I guess, and then dependent is the number of chairs. So again, pause the video if you as needed. Next example, Chad can usually catch at least 3 fish every hour. So what two varying quantities are kind of going on here? Probably like the total number of fish, and what else? Like, I know there's a very specific 3, but I think like as far as our variable, I think it'd be like total fish, right? Which I'm going to go ahead and spoil it a little bit. The total number of fish caught is going to depend on what? How many hours? You know, if he's catching 3 per hour, then so that's a pretty clear relationship. You know, you could easily make a table of values for that. So if we made a table, I'm kind of riffing here, calling an audible. So I'm just writing with my mouse very sloppily. So number of hours we'll call H. I know it makes no sense. And the number of fish we'll call F. So if you made a table, for example, it'd be like, well, if you put, say, 1 in the left column, 1 hour, how many fish would that be to kind of go along with it? Wouldn't that be 3? But let's say you fished for 4 hours, so you put a 4 over here in the left column. What number would have to be over here for the number of fish? If he's catching 3 every hour, wouldn't there be a 12? That'd be another pair of values in this left column, right column table. And then, you know, 5 hours, there'd be a 15. And you could put whatever pair of numbers you wanted as long as they worked together. Okay, but yeah, it would be like number of hours would probably need to be, or usually it's the kind of the general convention, the norm, to put this particular variable that's independent in the left column and the more dependent variable in the right column. Alright, let's get into some very important definitions in the grand scheme of high school mathematics. And then even if you want to talk about the keystones, these terms, this vocabulary, will definitely be on the keystones, and you're going to keep seeing these important definitions in future math classes. So I don't know, maybe you've already heard of these. The domain of, say, I don't want to get ahead of myself. But what would we be finding the domain and range of? You know, it'd be the domain and range of some kind of relation or a function. Okay, but again, let's just kind of, I don't know, let's just kind of get on with it, I guess. So the domain, all right, would be the set of all the x coordinates. Okay, and I guess more on that as we do examples, but if you've never heard of this before. So the domain of something is the set of all x coordinates, and then the range would be the set of all y coordinates. So kind of the baby elephant in the room, this vocabulary word can mean something else. You know, if we were finding the range of just a list of data, just like a big list of numbers, the range would be the difference between the lowest number and the highest number. But here it's a totally different meaning, so just kind of be careful about that, just be aware of that. So here it's domain and range, and the domain would just be all the separate x coordinates, and the range would be all the separate y coordinates. So easy, right? So here's an example, and again, like an example like this, exactly like this, could be on the keystones. Find the domain and range of these ordered pairs. Well, again, it's really as simple as the domain is just all the x's. So you make like a separate list of just -2, 3, 5, and 10, because all these ordered pairs go x and then y, x comma y. So the range would just be a separate list of all the y values, -1, -6, -8, -13, right? So easy. Number two, I mean, just take a second to think about that really quick. What would be, I mean, I don't want to go too fast, right? So think for a second. What would be the domain? What numbers would go in the domain? Wouldn't it be the -9, the -5, the 3, and the 12? And then the range would be 0 and 11 and -6 and 54. Because the domain is just all the x's and the range is all the y's. If I gave you a table, remember, a table is really just another way to show you a bunch of ordered pairs. 1, 1.4, 0.8, 1.2, so on and so forth. So the domain, right, I mean, let's work smarter, not harder, right? I mean, the domain would just be all of those. They've like literally separated the x's and y's for you in two different columns. So the domain would just be all of those, and the range would just be all 5 of those numbers. We can also talk about domain and range of a graph. More on that later. We're going to skip this for now. We're going to do like a follow-up lesson strictly about domain and range of a graph. It's a little bit tougher. Like, I would like to think that these examples are like so easy it's not even funny. Maybe it's a little funny. Or this example somehow even easier because they've separated the x and y's for you. But this gets a little bit tougher to wrap your brain around. So we'll skip that for now and move on to these other very, very, very important definitions. In fact, this one's massive, like function. But first, relation. A relation is just simply a set of ordered pairs. That's it. That's all it takes. A set of ordered pairs, which means like two variables, two quantities that probably have some kind of mathematical relationship. So it's a bunch of points, And how could I show you a relation? Like, what kinds of things would show a relation, some kind of relationship between two things? Well, you could give a list, and a list is what I call right here. This is a list of ordered pairs. So I could show you a relation as a list. I could show you a table and say, hey, look at this relation shown in this table. There's this thing called maps or mapping diagrams we might see soon. There's graphs. Like, I could show you a graph on an XY plane, for example, and say, hey, look at this relation. Look at this relationship between, say, x and y. And equations, Equations can also represent some kind of relation or relationship, okay? Now, a function is also a relationship between x and y. So a function is a relation. It's just a very special relation. It's not that special because functions are very common, okay? Like very, very, very common, all right? And so it's a relation where for every value of x, there's only one value of y, okay? So think about that for a second. For every value of x, there's only going to be one value of y. So that's very, very clear and important. But again, it's also very common. Like, if you had an equation like this same equation I showed you on the first page, y equals -5x plus 3, that means if this is going to be a function, that means like if you were to input some number for x, that means you would only end up having an output of like one certain number. For every number you plug in for x, you can only possibly get one number for y, one value for y. Which, is that the case here? Like, if you plugged in your favorite number for x, how many different numbers would y equal from that? Wouldn't you just get one? Like, if you plugged in, say, 7, like my favorite number, let's plug in 7, If x equals 7, wouldn't y only get to equal like one thing, like whatever negative 5 times 7 plus 3? That's only one answer. So yeah, this equation is absolutely a function. Again, functions are very, very, very common in high school mathematics, especially when what you're talking about is an equation representing that relation or that function. Okay, it's not tough at all for an equation to be a function, where for every x there's only one partner that can go with it. But tables, for example, kind of a different story, and maybe even graphs. So, sorry to kind of go fast here, but you know, this relation is also a function. This is not. You know, again, remember, for something to be a function, for every x, there can only be one partnering y. So basically, a pretty good translation is, in functions, x's are not allowed to repeat. Okay? X values not allowed to repeat. So look at over here. 1, 2, 3, 4. There was no repeat x's. But over here, this one was not a function. We had repeat x's. And that's kind of a really easy way to tell. You know, by looking at a table or a list. If we were talking about a graph, you know, and well, never mind. So how can you tell on a graph if it's a function or not? Like if there's any repeat x's, you know what I mean? Remember, for every x value, there can only be one y. And I don't want to get too detailed here. I don't want to like over teach this too much. But I don't know, let's analyze this for a second. So over here on this graph, you know, this graph contains a bunch of points. You know, we have this point with an xy pair, you know, and then we have like this other point that's an xy pair. I mean, there's an endless number of xy pairs on this graph. Now, do you think you think with all of these endless points making up this graph, do you think there's going to be any repeat x's? Like, do you think for a certain x coordinate there's going to be, what do you think? Like, this might be, you know, x equals -2, maybe. I'm just kind of, it could be. You know, like, what would the y coordinate be? And then, would there be any other, maybe that's a decent way to talk about it. Oh, I don't want to know the white color. What should we do here? Maybe pink. So for this random x coordinate, this random x value that we'll just say is -2, okay? And we'll think of this as -1 maybe, I don't know. Like how many, isn't there only one point? Like -2 comma whatever, you know, maybe -2 comma, you know, 1, like let's say this is 1. So there's only, I mean, it's not like there's also a point that's -2 comma 4 up here, or there's no -2 comma 0, there's no -2 comma -1, there's only this point for x equals -2. Just like for x equals -1 right here, there's only this point. It's not like, you know, maybe we'll say it's like -1 comma 1/2 ish. You know, it's not like there's another point down here for x equals -1, or up here for. So anyway, I guess the punchline is that there's a very easy test when you're talking about a graph, and it's called the vertical line test. So kind of write that down, vertical line test. And so it's a very easy, you know, process of just whether it's your imagination or your finger or your pencil, if you can slide a vertical line side to side across the graph, and your vertical line is only ever hitting the graph once, like hitting it once, hitting it once, hits it once, hits it once, hits it once. As long as a vertical line is only ever hitting your graph in one spot, it's a function. So this one over here is not a function because, like, look, this vertical line is hitting the graph in two different spots all over the place. So let's say right here this is x equals 1. Let's just say it is x equals 1. That means, like, you have this point on the graph, which is like -1 comma, I don't know, -3, and then but we also have this point right here, which would be, say, 1 comma +3. So vertical line test. So before we, oh, there it is, geez, right there. Sorry, it was already set to be written down right here, my bad. A graph is a function, so a graph represents a function is probably the better way to say it. A graph represents a function, like that relationship, if you can draw a vertical line anywhere and it only touches the graph in one point or one spot. Okay? Because that's like the graphical way to see if there's any repeat x's. Remember, x's are not allowed to repeat in a function. That's why this was not a function. So vertical line test, what do you think? Do you think this example passes or fails the vertical line test? Is a vertical line hitting the graph in more than one spot anywhere? I would say so, like there probably, and probably also there, and probably also there. So that's a no. What do you think? Do you think number 2 passes the vertical line test? It does. Do you think this one hits it once, but then right in here, yeah, in a lot of spots, it's hitting the graph in like 3 different spots. So that is a no. This graph does not represent a function. And then let's see, probably some more super easy examples. See, a lot of these examples are really easy. As we look to finish this up, remember, we're saving this for tomorrow or next class, or very, very, very soon, to find domain and range of a graph, But when it comes to domain and range of a table or a list, or whether or not these things are functions, like is this a function or not? What's the domain and range? A lot of these questions are like really straightforward and really easy. So the question here is, does this relation also qualify as a function? Are there any repeat x's? There's not. 10, 2, so that's a yes. If there's no repeat x's, then it is a function. How about number 5? Does this qualify also as a function? Nope, because we had repeat x values of 20. 20 can't hook up with 5 and 2. It's not allowed. Okay, this is what I meant as a map earlier. So these maps or mapping diagrams, and oftentimes, just to kind of throw this out there, I don't like that. Let's, bam, let's do that. So oftentimes these mapping diagrams involve these like bubbles. Okay, just to kind of, I'll erase them now. But which one of these mapping diagrams do you think represents a function? Remember, functions are not allowed to have any repeat x's. Like, do you think in this one there's repeat x's? You think there's any repeat x's here? A mapping diagram is, well, here's all the inputs. So -7 maps to 4. So like if you wrote this as a point, it would be -7, 4. You know? And over here, this would be 3, 9. So all of these inputs are mapping to all those outputs, basically the x's and the y's. So which one of these do you think actually qualifies as a non-repeating x function? If you're thinking x, you are right. So you're allowed to, let's see here, you're allowed to have repeat y's. Like I know this is like 7, 6, -1, 6, 0, 6, 8, 6. There was a lot of repeat y values, but that's okay, I guess. Last stuff. This is what I just kind of pointed out. You could have repeat y's, but it's not fair. So very last example, just another easy example. I don't think there's anything new here. What do you think? Which one of these which one of these lists, A, B, C, or D, represents a function? This totally could be a multiple choice question on the keystones, for sure. 3 seconds. If you said B, because we have 0, and then 1, and then 4, and then 9, with no repeats. Look, repeat 2's, not allowed. Repeat -1's, not allowed. Repeat x values of 1, not allowed. So yay, we're done. So that is section 3.5, focusing mainly on domain and range, and whether or not it's a function, it qualifies as a function of, tables and lists and graphs and mapping diagrams. And so we're definitely going to follow up on this next time, probably.